Hey everybody, Mr. White here. We are going to be talking about Newton's second law of motion today. So we know Newton's first law tells us that an object at rest will stay at rest, or an object in motion will stay at its current motion, same velocity, no change to speed or direction, unless acted upon by an unbalanced force. So in other words, forces need to be unbalanced to cause acceleration. Net force cannot be zero. Newton's second law expands on this by telling us how much force is needed to accelerate a mass and how much acceleration will we get. Now, more specifically, Newton's second law tells us that the acceleration of an object is proportional to the net force of the object and inversely proportional to the mass of that object. What that means is that when force goes up, so does acceleration. When mass goes up, acceleration goes down. They're inversely related. And I think we already kind of have an idea of this, right? If we apply more force to something, it's going to accelerate at a higher rate. Its velocity is going to change faster. If we add more mass to something, its acceleration is going to reduce. It's not going to be able to increase its velocity as much because it's just harder to move at that point. And we can see that reflected in the formula for this law, and that is stated as the acceleration of an object is equal to the net force applied to that object divided by the mass of that object. And we can write this a few different ways, and that's really helpful because sometimes we're not always solving for acceleration. So for example, I could write this as the mass of the object is equal to the net force divided by the acceleration of the object, or in probably the most common form, and many of you have seen this, the net force on the object is equal to the mass of the object times the object's acceleration. Now, we can use what we know about fractions to see the relationships between these variables. And like I said before, the force applied is directly proportional to the acceleration, and the mass of the object is inversely proportional. So that means that as mass increases, acceleration is going to decrease. If mass decreases, acceleration increases. And it makes sense, right? The more massive something is, the harder it is going to be to accelerate. We know that from Newton's first law. Now, if force increases, so does acceleration, and if force decreases, acceleration decreases as well. Now, typically I like to do math on the units as well because I like to show you the relationship between the different units of measure that go into making up our new measurement. And so in our case, we're looking at force is equal to mass times acceleration. That's one way we can write the formula. And if we put in the units of measure that represent those different measurements, we see kind of a weird relationship. It's not as clean as, say, speed, where we have meters over seconds, giving us meters per second for our speed unit. In this case, we see that newtons is equal to a kilogram times meters per second squared. And I know that seems weird, but a newton is in fact equivalent to a unit of kilograms meters per second squared. So if you see kilograms meters per second squared, realize that that is the same thing as saying a newton. And that does become handy later on when we do need to break force into components to combine with other things to get new units of measure. So for now, just keep in mind that 1 newton is equivalent to 1 kilogram meters per second squared. All right, so far there's been some relationships that we've talked about, and now we can actually kind of prove them using this formula because now we can throw some numbers in there as well. Now, so far we've talked about things with inertia qualitatively. We say more inertia, more mass, it's harder to accelerate. But now we can actually plug some numbers in and see this work. So for example, if I have something I want to accelerate at 1 meter per second squared, and let's say that that object is 1 kilogram of mass, it's going to take 1 newton of force to do that. Let's say I have 2 kilograms of mass that I want to accelerate at 1 meter per second squared. I'm going to need 2 newtons of force. For 3 kilograms, it's going to take 3 newtons of force, and so on. So not only do we know that things with more mass have more inertia and therefore resist acceleration more, now we can actually see, well, just how much force is it going to take for me to accelerate something at a certain rate. Now, if you're one of my students, you've heard my example of pushing a real car versus pushing a toy car. It's one of the ones I bring up quite a bit when we talk about inertia and Newton's laws. I think it's about time we actually see that happen. So we got to head for the parking lot. There you have it. Now, another one that gets brought up a lot is that net force and acceleration are always in the same direction. If net force is forward, acceleration is forward. If Net force is backwards, acceleration is backwards, and so on. And we can actually see how this works mathematically using Newton's second law. So let's say we apply a net force of 500 newtons to a 50 kilogram mass. If we plug that into our formula for Newton's second law, we can see that 500 newtons divided by 50 kilograms gives us an acceleration of 10 meters per second squared. Pretty straightforward. But what if we reverse the direction of net force? Let's say we apply a negative 500 newtons of force, so 500 newtons in the opposite direction, to that 50 kilogram mass. Well, when we run it through the formula this time, look what happens. We end up getting a negative acceleration, again, in the same direction as our negative net force. And so this helps to reinforce that idea that net force and acceleration are always in the same direction, because as you can see mathematically, there's no way to have those two variables have a different symbol. It's either going to be both positive or both negative. Mass is a scalar value, so it can't be negative. So if net force is negative, acceleration is going to be negative as well. Now, along similar lines, we know that no net force means no acceleration, and we can prove it using Newton's second law as well. If we were to plug a zero net force into this formula, we see that no matter what the mass, you are going to have zero acceleration. So again, no net force means no acceleration. Mathematically, zero over anything, over any mass, is going to give you zero. Now, sometimes we don't always want to do the full calculation to figure out what effects maybe more mass has on the acceleration of an object. We can use proportionality for this. So the way proportionality works, we just apply multipliers to the different variables rather than plugging in actual values into the formula. So it does save some time if you know how much something changes by. So, for example, how does doubling the force affect acceleration? Well, for one, when we're setting these up, we want to use a formula and we want to isolate the thing that we want to see the effect on. So, for example, in this case, acceleration, we want to know what happens to it. We're going to leave that by itself on the left side of the formula. Now, we know that we are doubling force. So I'm going to put a coefficient of 2 in front of the net force variable. We're not changing mass, so I'm going to put a coefficient of 1. And because this is an equality, whatever I do on one side of the formula, I have to do on the other. So I'm going to put the 2 over 1 next to acceleration as well. And that tells me that acceleration doubles if I double net force. Now, what would happen if we cut the mass in half? And we're going to do the same idea. We're going to keep acceleration isolated because we want to know what happens to acceleration. And so using the formula again, I'm going to put a coefficient of 0.5 next to mass, and I'm going to put a coefficient of 1 next to force because we're not changing force. And we can have to do that on the other side of the equality as well. And so we see that if we half mass, we cut mass in half, that is actually going to double our acceleration as well. And this is really handy when we want to do a really quick calculation to figure out the effects of one change on some other variable. All right, so here's some practice problems for you. Go ahead and pause the video, give them a try, and then you can let the video run when you're ready to see the answers. And if you're still struggling with these, make sure you get some extra help from your teacher. Now here's some proportionality practice. Again, go ahead and pause, try these out, and then replay the video when you want to see the answers. All right, well, that about wraps it up for now. If you have any further questions, make sure you get extra help from your teacher. Thanks for watching. Have a good one.